Hi everyone. So I'm going to talk to you about CHERI and the work that we've been doing on CHERI and Linux. So I'm going to go through some history, how we got to where we are, what we're doing at the moment, and some ideas what we're going to do in the future as well. So I'm going to start with a history of capabilities. Capabilities are pretty critical to understanding what CHERI is, because CHERI stands for Capability Hardware Enhanced RISC Instructions, which probably doesn't make a lot of sense to anybody unless you understand what a capability is. So what it does is also there. It extends ICEs to add capabilities. So capabilities were first mentioned back in a paper from 1966 by these guys, Dennis and Van Horn. It's a really interesting paper, this. It sort of summarized a lot of the stuff that was going on at the time around the development of multiprocessor computing. So you'll find in there things like, definitions of segments. You find definition of processes, things like even fork, all the stuff that you see coming up in the Unix whenever it started to be developed in about 1969. But one of the things they did very much at the time concentrate on was security. So they were very clear that computations didn't interfere with each other. And what these guys did was take some earlier concepts from stuff that was happening around the really early computers like Atlas, Rice, Burroughs machines, stuff like that. And they generalized them into what they called capabilities, where processes need to own capabilities to be able to do something on a system. So the way they described it was, each capability has some sort of reference and rights. So a capability is an access control object. So previously it was generally defined for memory, but they extended it to other things, I/O, everything else. But we're going to concentrate on memory capabilities today, because that will lead on to the CHERI stuff. So you've seen even in those days, they're starting to think, we have a reference to memory, and we have permissions for how we can use it. So obviously, read, write, execute, stuff that you see today. So we can start to define what a capability is. So a capability is an unforgable, transferable token that authorizes the use of an object. And we're talking about here a type of capability called an object capability. It encapsulates a reference to an object and the rights to use it for accessing it. Now, the way it was conceived at the time was they had this list of capabilities that each process had access to, called the capability list or C list, and then an indirection to the resources. So in the case of memory, there was an indirection through the C list table to the memory, to the segment table, as it was. And just bear this in mind, because whenever we got onto the hardware implementations of it, this is just an example of some of the capability machines that have been developed. And you can see the long time frame as well. We're starting here from the 1970s, but actually there was slightly earlier ones as well in the US. So we have the CAP computer from Cambridge University, which was developed in the early 70s. We had the first sort of commercial, well, probably first ever commercial capability-based system, which was the Plessey System 250. Now, this wasn't a general purpose computer. This was originally built for the military for messaging communications, real-time communications. But it did have all the concepts of what we think as a modern computer. It had virtual memory. It had 8-core SMP. It was a pretty far ahead machine for its day, and it was used a long time. It was also built to be ultra reliable. So I think the original design spec was mean failure time of 50 years. So you don't get that much anymore. But anyway, it was deployed successfully and ran for a long time. Less successful was something like the Intel IAPX 432. So this was also a capability-based process that Intel developed. Again, this was originally done as what they thought was going to be a replacement for the 80 series. Didn't happen that way. It ended up being used for very niche applications, all around, again, reliability and security. But it suffered from really bad performance, mainly because of this indirection effect. More lately, we have the Morello chip. So this was a research chip done by ARM in conjunction with the UK government, where they took an ARM Neoverse N1 and they retrofitted on CHERI on top of it. So they had about a year to develop this processor, which was really short time scales to get something this complex put in hardware. They did a really good job on it, but they obviously had to make some compromises in terms of the design when doing it. But we still use that chip today because the latest version of CHERI have taken a lot of concepts and taken them from a superset down to a what we think now is a more commercial-oriented set of capability structures, which I'll get into in a bit. But the Morello had a much wider set of capabilities, so we still use it for research. There was also a lot of software work done over the years, various operating systems. So some you've probably never heard of. You can see they're mainly focused around high levels of reliability. But, you know, they even go to modern SEL4. And this year, there's even CHERI SEL4. But we're here for Linux, so. You also see some vestiges of capabilities still in the Linux kernel as well. So socket file descriptors fit the sort of capability model. You have something that you pass around that has rights associated with it. Kernel capabilities, maybe not so much what I would call a real capability, but we have them. You can even think of them like a page table entry as being a capability, because you have a reference to memory and you have associated permissions with it. So, again, in the broadest sense. So, what is CHERI? CHERI is a new implementation of capabilities. Now, it's a security technology that is designed to be scalable, which means we can use it in everything from the tiniest microcontrollers up to server-class chips, and we're already doing this. Microsoft produced a microcontroller version called CHERI, and you can see it's gone the whole way up to the ARM Morello, the Neoverse. So we know it's very scalable. It's deterministic, so CHERI doesn't rely on any secrets being kept. You know, you don't have hidden bits or anything. There's no hashing, there's no keys, anything like that. It's very much a hardware-software co-design technology as well. And the variant that we look at is called capability-based addressing. There's no C-list involved, so we don't have the indirection and the performance issues that plague the older systems. The other thing it does is extends existing ISAs. So CHERI already has been, it was originally developed on MIPS. It was then put on ARM. Currently, most of the development we're doing is on RISC-V, and there's even an initial sort of a sketch of it, if you want to call it that, on x86 as well. It's what we call a hybrid capability architecture. So it's designed to work with existing systems as they are. So it'll function quite happily with MMUs, hypervisors. So on a capability-based addressing system, what we're doing is replacing integer address pointers with capabilities. And in the case of something like a system with an MMU, like Linux system, we use virtual addresses in here. So it plays nicely with existing hardware. It's backwards compatible in that it's, you know, you have to use the instructions in your code to get the benefit, but you can still run your systems and your software as is. You could take a binary, run it on a CHERI system. It'll run, but you don't get the CHERI benefits. It's had 15 years of development, so it's been going a long time. Originally started by a company in the US, SRI International, and a university in the UK, University of Cambridge, funded by DARPA. It's had ongoing development for many years, funded continually by DARPA, but also by private companies as well. And at the moment, there's also an industry body called the CHERI Alliance, so I have to give them a plug. And they're sort of the focal point at the moment for CHERI development, working groups, software repositories, stuff like that. So there'll be a link in the slides when they give that. So the design goals for CHERI are to provide memory safety, even for languages like C, C++. It also benefits other languages, including Rust, and also provide fine-grained, efficient compartmentalization. And fine-grained is important. I mean, we already have coarse-grained compartmentalization in our systems. You know, you have the MMU that will isolate processes, and you have vertical integration in terms of your rings or modes like supervisor and user mode. But these are coarse. CHERI is designed to be very, very fine-grained, down to the byte level, if you wanted to go there. As I mentioned too, it was also meant to work with existing software bases and systems, or as easily as possible. Now, the ideal was to get a system that you could just put in and software would just run, but never works like that. So then they said, oh, it's just a recompile. Well, yes, it is in some cases, particularly for application code. If you have well-written C, C++, actually the modifications, if any, that you have to do with a CHERI program are extremely small. As an example, they took KDE. They get it running on a CHERI system on Morello, and total lines of change of code accounted to less than 0.02% of the code base. And from the guy who did it, he also wasn't sure whether that included comments. So, yeah. Now, when you start to get a bit more into details, particularly with things like language runtimes, JIT machines, and down in the operating system, memory allocators as well, things like that, then where you're dealing directly with lots of pointer manipulation and access to memory, then you have to make quite a lot more changes. And obviously, what we've been doing is looking at Linux, amongst other operating systems. We've also ported FreeRTOS, Zephyr, I'll say SEL4, and some others in the works as well. So, digging into the details a bit more, what do we do? Well, CHERI modifies the ISA itself. It extends it with additional instructions that allow you to manipulate these capabilities. So things like create and other things that you'd normally expect to do with a pointer, like increment, stuff like that. So arithmetic operations. The architecture itself, hardware, has to be extended to include this new hardware type of a capability as well. And then in software, as I said, we replace pointers with capabilities. And I say we can do backwards compatible. We can have what we call integer mode, where we have normal pointers, and we can have capability mode. And we can actually mix them. There's a system called hybrid, where we can annotate pointers in code so that some of them are capabilities, some of them are not. But we generally don't encourage that model. So we tend to go straight for pure capability code and integer code. And in terms of when the CPU is running, particularly on RISC-V, we do a mode switch to go into CHERI mode. And what that essentially is for is to save on encodings in the instruction space, because we reuse things like loads and stores to now become capability authorized loads and stores. Even when you're running in backwards compatibility mode, so non-CHERI pure cap mode, as we call it, all loads and stores, access to memory are always checked. And this is fundamental thing on a CHERI system. Every time there's an access to memory, it's checked against an authorizing capability. So we have program counter now, which is a capability. And for non-CHERI PureCap code, we also have a default data capability, which means that even backwards compatible binary code, we can still constrain. We can set where it can execute, and we can set what it can see in memory. So, which is useful if you've got a binary library and you want to include it with into a more secure system. So in terms of implementation, what do we do? So a capability is an address, as I said, but it's also now extended by additional metadata. And you have to think of capability as a single unit. So the address, bounds, permissions are single unit. Now the bounds are upper and lower memory bounds, because we're talking here about memory addressing. Permissions, you have your read, write, execute, as you've seen. We also have additional permissions like whether you can store a capability to memory or not. So there's things that we want to control, but I won't go into the details here. So all the registers in the system are extended from their natural width. So there's an example of a RISC-V 64-bit system. Registers now become 128 bits. And within memory, pointers now become 128 bits. And we have to carry this the whole way through the memory subsystem. So things like caches, for instance, L1, L2, L3, all now have ability. And we have this additional bit called a tag, which is a sort of out-of-bounds signal, which software generally doesn't interact with. And what the tag does is tell you whether, say, your register is containing a valid capability or not, or whether a memory area is containing valid capability or not. So it's a tagging architecture in memory, but only a single bit for every 128 bits. And it's interesting, going back to the past again, somebody predicted this was going to be the case in 1974. One of the other things I should mention is that the bounds, we're expressing here high and low bounds in memory. And you can see, obviously, we're squeezing them into quite a small number of bits. So originally, capabilities were 256 bits because they encoded the full 64-bit lower bound, 64-bit upper bound. But one of the innovations of CHERI is to use a compressed format for bounds. So we use a Mantissa exponent system, which loses some resolution, which on a virtual system, it's not too much of a problem. But obviously then we can make capabilities much more smaller. There's also rules to how we can use capabilities. So we have the provenance rule. So you can only create a capability using another capability. So you have to know where they come from. And this applies across the whole system. We also have a property called monotonicity. Now we can only ever attenuate the rights, bounds, permissions on a capability as well. So we have to use a capability to create another capability, but the capability that we create can only be more restricted or equal to the capability that we started with. And this is really important when you start to think about how it's used and how it's used for compartmentalization as well. We also have a runtime sort of rule, which is called reachable capability monotonicity. And this means that within a set of code that's operating within a compartment, say, you only have access to a limited set of capabilities and you can't go outside of that set. So you can't increase your bounds when you're inside a compartment. So one example of going outside this could be, for instance, if you take an interrupt, because you obviously then have to have a different scope of where you're executing from. So to start to make this a bit more concrete, how the system operates is whenever you boot, you have access to what we call the infinite capability, root capability. And this is generally stored in the program counter, the PCC that I mentioned earlier. Now the PCC, when it starts, has access to all of memory and it has all permissions. So this is where we start from. So then what we can do in the code is use that capability to start building subset capabilities. So on the diagram here, I've represented the bounds of the memory vertically. Permissions are marked in the bottom, and you can consider each of these ones on the left as a capability. So we start with our infinite cap, and then if we want to create 2 regions in memory, say 2 compartments, we would then break down into new capabilities. So you've got a region 1 capability and a region 2 capabilities. We might also choose to restrict their permissions. So say region 2 is execute only, it's code. So we set it to read and execute, no writable permissions. Region 1, well, we might store data in as well, but we can derive down another capability. So most of this is done by the compiler, all of the heavy lifting. So for instance, whenever you declare a static array in C, the compiler will generate a capability for that. It'll say, right, here's the array, the bounds of it are here and here. So you can start to see how you get memory safety. Because if you try to write outside of the array bounds, you'll get an exception. You can also set an array to be read-only or read-write. So things like executable stacks, we just remove the execute bit. We constrain the stack frame to just the bounds that we want. Okay, so CHERI on Linux. Why do we want it on Linux? Well, obviously one of the things we want to do is memory safety. Linux is written mostly in C. C's not a memory safe language. We would like to put memory safety in it. Good thing to do for a start. User space, C++ as well, suffers the same issue. As I mentioned, the compiler does most of the heavy lifting for this. Not all, but most. Capabilities are interesting as well from a security point of view because they actually allow us to implement least privilege as well, unlike any other technologies really, or many other ones. And we can use this with the compartmentalization. So as I mentioned, we have our coarse-grained compartmentalization at the moment. However, what would be really nice would be to put fine-grained compartmentalization into Linux. So one example of this would be to compartmentalize user space libraries, for instance. We've all seen recently supply chain attacks on libraries where people try to deliberately pollute open source libraries so that they can attack other things. So with a Linux system, we can put a wrapper, put a library into a sandbox, mostly automatically, which can constrain its access and its entry and exit points. So that helps out. Obviously, things like mixed language applications as well. If you're mixing things like Rust and C or Python and C or anything else where you have older memory unsafe languages and you're mixing them with a nice memory safe language, we can start to get more of the guarantees back on memory safety. And we can, again, isolate components of those applications. Within the kernel, we can do the similar thing. For instance, modules. Obviously been a source of security problems in the past, many of them. Network subsystems, other subsystems, we can put them in sandboxes. Now, a couple of years ago, the HACC analysis, that project, did analysis on the kernel. So this is just the kernel. They looked at all the CVAs. They looked at where memory safety can help, where compartmentalization can help, and how it could reduce CVAs. So you can see immediately, with a memory safe system that's compartmentalized, they reckoned 87% of vulnerabilities could be reduced. So we see that as a pretty important thing to try and achieve. So where are we currently? Well, about 2 weeks ago, we got a kernel 6.16 working with pure capability mode. So this means that every pointer in the kernel is now a capability. So originally, there was a couple of proof of concept and then a more mature Linux kernel port. So there was an original proof of concept port to CHERI sponsored by Huawei. So they sort of proved it would work with Linux. On the Morello project, then they developed a Linux kernel as well. Though theirs was slightly different in they used, as I mentioned, hybrid mode earlier. So most of the kernel was still running with integer pointers, but the syscall layer was running with pure capability mode. So we started with the ABI, actually, they developed. They put a lot of work into it. And then we started doing a clean implementation on top of that. So, as I say, at the moment, we have a nice, clean V616. We would not claim it's perfect. What we're aiming at the moment is functionality. We want to get the basics running. Then we're going to go on to the more advanced security concepts. The more advanced concepts have been proved already on BSD, not on Linux yet. There is a more advanced version of CHERI BSD, free BSD, with a lot of the capability isolation support that I've already mentioned. And we're working to work towards that for the Linux kernel and deal with all of the Linux specific stuff as well. As I say, we're looking at functionality at the moment. So we have our memory spatially safe kernel. We're testing obviously against LTP. We've not got a good pass rate on the LTP. We're running a lot of code already on it. We're working through subsystems, and it's looking pretty reasonable. On the user space side as well, we have a pure capability user space currently. So we have a Yocto build that builds a relatively simple user space. But again, it's all running with capabilities instead of integer addresses. There's still some major bits that we have to tackle. We don't have glibc yet. We're using Muzzle. We do have things like dynamic linking and everything else in there. And from my company's point of view, we're concentrating on the sort of core infrastructure. So we're looking at the kernel and core libraries at the moment. So this is just an example of the work that we've been doing over the last month. So to get things running, it just gives you an idea of where we are at the moment. So things like module loading, yep, we've got that working. Some things obviously have more complications. When we start dealing outside of exclusively within the kernel and interacting with user space and existing frameworks, then we have to think about how we're going to deal with the change in the ABIs between capabilities and what were just unsigned longs previously. But we have, let's say, we're really up to pretty reasonable functionality. We have network working, BPF and eBPF, I'll get on to in a minute. Obviously, we have things like USB, PCIe, that's all working fine. We've had graphics running. We've got a rather dated X11 system working, but it's fine. And we've already started some optimization work, particularly around the copy to and from user side. And memcopy as well, because we can actually get some accelerations on a CHERI system because we can do 128-bit loads and stores on the 64-bit system. So there are ways that we can get some performance. Obviously, there's a lot of other work going on around all of this. At the same time, we're developing things like the LLVM compiler. We're developing things like QEMU to be able to easily run and test these stuff and get more visibility of the code while it's running, and the tracing of that. And if you look at the CHERI Alliance website, again, there'll be a link here. You'll be able to see all of the code as it progresses. So, as I mentioned, for CHERI and Linux specifically, we need a new API. So we have this thing called the Pure Capability API. Obviously, now we have to think about things like between the user and the kernel, about syscalls, passing capabilities. But the thing is, if you get a capability from user space to the kernel, incoming, then obviously you're limited then in the kernel by the stuff that the user space has supplied you in terms of bounds and access permissions. So you're already starting to constrain the interface and the memory use between the two. Similarly, when you go from the kernel to user and things like mmap, you can limit bounds and permissions that you give, for instance. Challenges, well, it's mostly all right. Most of the changes are pretty basic, but there are some fundamental changes. So particularly things like unsigned long in the kernel. There's no differentiation in the kernel between a pointer and an unsigned long, an integer value. So it's used everywhere. Now, for our compiler to effectively add the capabilities, we need to change those unsigned longs into pointer types so that the compiler knows how to deal with them, that they're capabilities. We obviously have to deal with alignment issues and stuff like that due to the change size of the capabilities. And we also see within the kernel some misuse, particularly of pointers. We get things like function pointers being used or switched over to being data pointers. We get pointers with bits being set here and there to indicate stuff, which obviously doesn't play very nice with our capability system. So there's some cleanups we have to do to get it to run. We obviously have to think about all the time about how to minimize the changes to the kernel APIs. And we have one eye on upstreaming, which we'll get to later as well. So in terms of the future, so the next thing we're going to look at is compartmentalized module loading, which I mentioned earlier. So how do you isolate modules from the rest of the kernel so that they're constrained? It's an interesting problem. You obviously, when you think about it, the modules have to have quite a lot of access within the main kernel. So the other big ticket item is eBPF. So eBPF, and particularly whenever the bytecode's compiled in user space, has no concept of capabilities and constraining memory. So that's something we're going to have to look at. We also want to do it in a way that's backwards compatible. So we always have to think about, if somebody just has some code that has some bytecode in there already, we still want to be able to run it. But we want to, similar user space, be able to provide a new sort of more secure version as well. As I mentioned, working CHERI BSD is helpful here. The other thing we can do more effectively is MMU-less Linux as well. One of the big blockers in MMU-less Linux has been the lack of isolation between processes, or hardware-enforced isolation. Now, one thing's, obviously, the MMU provides two things. It provides isolation and it provides translation. So one of the things we can do with CHERI is take over that role of isolation from the MMU and use CHERI to separate the processes. We still have to deal with the memory issue, but there's some work ongoing in academia now. There's interest that CHERI is sort of refreshing some ideas and getting people to look back at these sort of issues. So it'll be interesting to see what happens in this space. But it's certainly something we want to do at least an initial proof of concept on. The other thing would be single address space Linux. So still using virtual memory, but now again we're separating the role of the MMU from its isolation versus translation role. So we use CHERI to do the isolation, we use the MMU to do translation. Now in particular workloads, this has got a lot of benefits. Particularly where you're sharing data, because now you don't need to keep swapping TLB entries to refer to the same data. You can keep the same one. So the TLB thrashing is something we're looking to see whether we can avoid. And this is when you have lots of multiple independent processes targeting shared data. So finally, we always get asked about performance. Everybody says, well, what's a modern CHERI CPU like? So within Codasip, we designed a CHERI CPU from the ground up. So rather than retrofitting it on an existing CPU, we actually did a design where we considered capabilities right from the start. And what Codasip, my company, does is also we do IP core design, but we do configurable IP core design. And that means we can, for instance, switch on and off CHERI when we build a core, which is really nice for performance comparisons as well, because we can look to see what's the impact of a CHERI system compared to what's a standard application processor. And I've been allowed to share these. So in terms of silicon area impact on our core, we have less than 5%. Our frequency, maximum frequency of operation on the core between a CHERI and a non-CHERI system, difference is 0. We can run it both at the same speed. In terms of the instruction overhead, so we measured this across quite a wide workload now. It's around 3.8% in terms of the additional instructions CHERI adds. In terms of performance overhead, at the moment we're seeing less than 5%, and we're still going through optimization on this. So you can see a CHERI system compared to a non-CHERI system, we're getting pretty close in terms of performance for a lot more security robustness as well. And we think we've got further to go as well. So just to wrap up, going back to the original Dennis and Van Horn paper, they deliberately talked about a lot of properties that they would expect a multi-programmed computer system to have. One of the things they particularly point out is that they must evolve, and this is really what we're looking to do with CHERI. We want to evolve hardware and software to really improve the security. Thank you.
Questions?
Thank you. Great talk. I'm Scott Constable with Intel Labs. You mentioned DARPA several times, and it's really clear that they care a lot about memory safety because every few years they begin a new memory safety program. And their latest one is Tractor, the Translate All C to Rust.
Yes.
If DARPA's successful or nominally successful, what role do you see CHERI playing in an environment where a majority, even a vast majority, or all C code has been replaced with Rust?
Yeah. First of all, the question mark there is this possible? I mean, AI translation. Yes, I can see it can work for some code, but obviously trying to understand the thinking behind code is difficult for an AI system, I think. Being able to understand the whole concept of what's being done. So I'll say that first. Secondly, we don't see Rust and CHERI as being in conflict. In fact, the CHERI language itself is being modified to adapt to sustain Rust or CHERI as well. So we have a concept of pointer and different pointers in the Rust. So there's bits in Rust where, for instance, obviously you've got your unsafe regions, which more particularly impact the very lower levels if you're going to implement an OS, for instance. But there's also other things we can do. I'm not a Rust expert, but what I've been told is there's areas where Rust can't determine sort of the safety, so it puts in software checks. These are the things that we can put in with CHERI to give enhanced performance there. So we see the combination of CHERI and Rust together actually being really good, and it's something we are putting effort into. There will be a CHERI Rust compiler for this stuff. But if Tractor isn't successful, you have trillions of lines of C code out there. Trying to convert those all to Rust, that's a big task. The other thing CHERI allows us to do is do this incrementally. So, we can, as I say, mix Rust, C, and still get these memory safety things. The other thing going on beyond that is this concept of compartmentalization. And this is the bit that actually I find more interesting in CHERI than the memory safety. Memory safety, yeah, it's good. We know we need it, but as far as I'm concerned, it's now a pretty much mostly solved problem. Obviously not for the existing code that's out there. Compartmentalization I find more interesting. Being able to get least privilege in software is a real big step forward, I think. And I don't think even any of the current languages we have really take this into account. I think we would have to do a further evolution of language to be able to support this whole concept nicely. So,
All right, thank you.
Hi, thank you for your talk. Have you seen Arne Bergman's talk about the future of 32-bit Linux?
no.
He mentioned that MMU-less Linux is probably going away pretty soon because there's Zephyr now and there's no need for Linux. And then I have a question. What about the memory increase on systems?
There is memory increase, you're right. We haven't measured this on Linux yet. So at the moment, we're just at the stage where we're doing more advanced benchmarking, system evaluation. So I can't give a figure on the memory overhead. You have two aspects of memory overhead. We have to store tags for a start, but that's not a big concern because that's typically about 1% on memory or less. We have a tag unit on before DDR, for instance. In terms of pointer increase, it's very code dependent. If you have a JIT machine, for instance, that's firing around lots of pointers, then yeah, you're going to get an increase in memory. If you've got a computationally based thing, then no. Yeah. And in terms of 32-bit MMU-less Linux, we still see quite a lot of people asking it, particularly around things like routers and stuff like that. Lots of networking-based appliances. People want cheap, very cheap network routers. They ideally want Linux, but they ideally want to bring the price down on the silicon. So this is sort of where we see the niche for that sort of system. But again, if you have the isolation in there, if we solve the memory issue, then it becomes viable. It keeps the cost down.
And plans to remove MMU-less support from Linux. So talk to him if you want to. If you have interest in it. And regarding the compiler, which compiler do you use, and is this work being upstreamed?
So we're using LLVM, and it's currently in the process of being upstreamed. It's the first bit of CHERI that's starting to go up. We'll probably discuss it later in panel session, but we have to take various different approaches to how we upstream the stuff. Hitting people with CHERI into a big project like that is, well, a shock to say the least. So what we've been doing is upstreaming the sort of infrastructure that we need to make CHERI happen. And some of that is starting, I think it'll go in an LLVM 22, some of that. So we're starting to see it come through, which is really nice. So.
I also have a question. So you mentioned about the kernel 6.16. So you just said that, okay, you have a basic support, but when it comes to compartmentalization, which is actually also agree it's more interesting part, what level are you? Are you running everything in like one compartment still, or?
Yeah, at the moment we're just starting to look at compartmentalization on Linux. So we'll probably start with user space first, library compartmentalization. That's been sort of more well understood from the CHERI BSD work. So we can probably quite easily translate that over to Linux. I would say the other thing that we're looking at is module compartmentalization, which is sort of linked in terms of linking, symbol linking and stuff like that. But obviously we have a different scope slightly in this. So those are the two things we'll look at in terms of compartmentalization.
Yeah, kernel compartmentalization would be very nice and interesting, but it's going to be very challenging.
Yeah, it's certainly going to be very challenging. And there's lots of stuff we'd love to compartmentalize. The idea, you could take this to extremes and eventually have a kernel that's effectively microservices. But yeah, it's going to take a long time to get there.
Do you think it's kind of even realistic, or would it really require like 80% of rewrite of Linux kernel? I mean, given that it never has been considered in the design, I mean, this is pretty fundamental change.
Yeah, I mean, based on the work that the HackC guys have been doing, we think it's at least to some extent achievable. You know, you're right. If we want to do this completely from scratch, in fact, I'd do an operating system. You know, if you had unlimited resources, you do an operating system that's completely compartmentalized. You wouldn't even have things like supervisor user mode or, you know, MMU-less separation, because you could do the whole thing in compartments. You obviously couldn't do that on Linux, mainly because of the GPL exception. So if we get rid of the supervisor user mode split, yeah, that's not going to work. Unless we get another exemption for compartmentalizing or compartment switches for being non-linking. So, yeah, I'll say you can take it to extremes, but...
Any other questions?
So in terms of the community, it's what's your kind of relationship with the Morello project? Are you like joining forces with the upstreaming?
So, yeah, I mean, the CHERI community is actually pretty tight-knit, actually. All the guys who worked on Morello, you know, things like the University of Cambridge group, for instance, we work really closely with those guys. We work with the CHERI guys as well, came from Microsoft. A lot of it's still very US, UK focused as well, but it's still the same sort of companies, but we're expanding this out now. There's a lot more commercial interest in it now, and a lot more people starting to get involved in it. I'd say if you look at the CHERI Alliance, you'll see all of the companies involved, and you'll get an idea of the sort of the community and how it's growing. So,
Any other questions?
Hi, outside of the change from just ulong to pointer types, what does the code changes look like?
I would say mostly it's to do with pointers. I'd say things like structures, alignment of structures and stuff. We have to do a lot of work on. Most code, as I say, particularly in user space, will go through. There are some sort of gotchas that we have hit. So things like on the wireless stack, for instance, in user space, they were setting bits and addresses to indicate invalid sort of usage, stuff like that. We get hit occasionally with. We also have the two big packages we're sort of coping with at the moment are something like libzstd, the compression library. Now it makes assumptions for doing acceleration, you know, for performance acceleration, and how things like overflows, addresses and stuff like this. These are the sort of things that we do have to think about, but they tend to be quite rare cases. In that case in particular, we have to go right back to the algorithm and see what it's doing to be able to engineer in CHERI into it. Other things, we typically just run them. CHERI, I would say, is a brilliant ASAN, address sanitizer, memory sanitizer. If there's a bug in your code, it will find it. So even for debug, I would thoroughly recommend it. And this is what we tend to do. We run the user space or any other code. We get an exception. We track it back to the source and then figure out. But it does tend to be mostly just misuse of pointers. So, as I say, nice, clean, modern C or C++ code, we have usually very little problems with. Older stuff that does a lot of clever pointer manipulation and all like that, yeah, it's a bit more work.
Thank you.
Any other questions?
Hello, thank you for your talk. I'm just wondering, are there any software emulations available tools so that we can try it out ourselves?
Yeah, so at the moment we're pushing, so all this stuff's going to be open source. At the moment we're pushing up our kernel. So as I say, if you look at the CHERI Alliance, there's already a v6.10 kernel up there. We're just about to push up the 6.16 one. There's also a QEMU that is CHERI aware. So you can take it. We're going to push up scripts as well to allow you to build. So we'll essentially push the Yocto build system up. which builds all of the toolchain, the SDK, QEMU, and everything else, and allows you to just launch and run it. So that'll be the easiest way. Once that's up, that's the easiest way to get into it and use it. We have some companies already testing it, pipe cleaning it. We're cleaning up some of the code, but yeah, that'll be the most accessible route.
Yeah, and just one more question. With regards to, you mentioned address sanitizer, and how does it compare with like memory tagging extensions, so MTE, and
yeah, so
other hardware initiatives? Yeah,
this is where the deterministic bit comes in. You know, MTE uses the 4 bits, which are sort of kept hidden, but you've got the risk there of things like side channel leakage. CHERI, we don't rely on anything. I guess you could say they're both tagging architectures, but you know, we're only relying on one single bit of tag for validity bit. We're not relying on anything else more than that. So yeah, and in terms of granularity as well, as I say, we can basically put a capability that can, you know, address a single byte if we wanted to. Not usually very practical in your code. You'd have a lot of capabilities in there, but could be done. Or even a single function if we wanted. So,
thank you.
Hi, thanks for your talk. Just a few notes. I'm Kevin from ARM. I worked on Morello. So if you want, there are quite a few options actually. If you want to try CHERI/Morello without hardware, there's something called what's the name? CHERI seed, which allows you to compile your code into like some kind of CHERI emulation mode, but you can just run on any machine. Yeah, I can provide some links if you want. And yeah, I actually had a question for Carl on the performance, of course.
Yeah.
The 5% figure, is it comparing the baseline core running normal RISC-V code, right, versus the core with CHERI and running in full pure cap?
yes. Yeah. Okay. All our code that we've been working on is all pure cap. So we haven't done a hybrid code at all on CHERI yet. Okay. I should point out too that the kernel, so in Codasip we've been working on RISC-V, but people are taking our kernel currently, putting in Morello support as well. So it will be able to run on the ARM platform as well. As I say, we use it very heavily for research. Yeah, these guys did a great job, particularly on the Linux ABI and stuff. So yeah, we've reused a lot of the work they did.
Thank you. It's great to see all of this come together.
Yeah. Yeah.
Okay, I think we're running out of time, so I would propose that maybe take it over to a break. So we have to move to the next speaker. So let's thank Carl once more for the talk.